Welcome everybody to this week's edition of the Oxford Discrete Maths and Probability Seminar. It's a huge pleasure to have Duncan Dauvergne, who's going to talk to us about geodesic networks in the directed landscape. Over to you.
Okay, thank you very much for the invitation. So the goal is to talk about essentially geodesics in random planar geometry. And so the directed landscape is this scaling limit that arises in lots of different models of random planar geometry. So in the first part of the talk, I kind of want to introduce the object, and please stop me and ask many questions. The stuff at the beginning is typically more important than the stuff at the end. It is maybe not the most discrete talk overall because there is but there's going to be a lattice on page 1, and there will be graphs later on. So let's begin. Okay, so what are we trying to understand? Okay, so let's look at a model of a random metric. Okay, so the idea is how can we define a random metric where basically paths going through disjoint parts of the metric have independent lengths. So I'm just going to take Z2. Everything I'm going to do is on the plane. I'm going to take Z2 and I just put IID edge weights on Z2. So in this example, we have, say I flip a coin on every edge. The blue edges get weight 1 and the black edges get weight 4, say. Okay. And then now I have a random weighted graph. I can look at graph distances here. Okay. So here, for example, I have my 2 points P and Q, and you can't see the blue and black underneath there, but this is the geodesic between these guys, and the distance in this graph is 9, for example. Okay, so the idea is we want to look at models like this and try and understand distances between points that are far away from each other. Okay, so let's look at a simulation. So this is this is another model of first passage percolation. So we're just looking at Z2 with IID edge weights that are, just flip a coin on every edge equal to 1 or 2 with equal probability. And this is the geodesic between 2 corners of this particular box. Okay, so we've sort of embedded the lattice with I think this is a spring electric embedding from Mathematica. Okay, so you should ask, if we're trying to prove something about this, what is supposed to happen for a model like this? And you can run simulations and notice a couple of things. We'll come up with heuristics as well. So the typical distance between, say, 2 points that are order n apart in the usual L1 metric, okay, the typical distance is still going to be order n. Okay, it'll be like a constant times n for some constant that we don't really know what it is. Okay, and so what we're going to care about are the fluctuations around this. So what's interesting here is there are fluctuations that live on a different scale than the usual square root n scale. So the fluctuations are typically order n to the 1/3 in these sorts of models. Okay, and the other thing you can ask about are the fluctuations of the geodesic itself. So the best possible path between the 2 points. And this geodesic tends to wander in an order n to the 2/3 window around the straight line between the 2 points. So it's not really happening in this particular simulation, but in theory, of course, it could wander all over the plane. Typically, it'll kind of follow a straight line. Maybe you'll have small backtracks here and there. Okay. Okay, so here's the idea. Say everything a little bit more precisely. So take one of these models, and let's look at distances between points that are order n apart. Okay, and what we're going to try and do is, conjecturally imagine the best possible understanding of the fluctuations in such an object. Okay, so because we're looking at distances in the plane, we have 2 coordinates for each point. And so we can potentially extract like a 4-parameter random field in the scaling limit. Okay. And what are the coordinates that we should look at? So we're going to have two kind of distinguished coordinates. The second one is a time-like coordinate, that's S and T. Okay, and that kind of, here, these are on the order n scale, so all points are going to be order n apart. Okay, and the x and y coordinates live on this lower order n to the 2/3 scale. So the reason we're looking at distances like this is because what you can ask is, well, in a picture like this, when would two distances be correlated in an interesting way? Well, they're going to be correlated in an interesting way if there's some reasonable probability that the geodesics overlap. Okay.
Just a quick question that's come up in the chat from Sergey. Why is it possible to embed this random metric on the plane?
Okay, so you shouldn't think of this. So we're just going to be working on Z2. Okay. So we're sort of in the plane to begin with, and we just start with Z2 and we start with Z2 and then we just assign edge weights to everything. So we're not trying to look at an actual isometric embedding into the plane. That's not going to exist in that case.
So maybe Sergey was asking about the picture, but I think Duncan was saying that the picture is kind of some approximation of embedding it in a
okay, yeah, the picture is absolutely an approximation. Yeah. The picture is Mathematica doing some particular approximation. It's not my simulation, so. Okay, so yeah, I was explaining why we're looking at n to the 2/3 in this direction. So the idea is, in order to see interesting correlations between distances, we see interesting correlations when geodesics have a chance of overlapping. So because everything is kind of happening around some main one-dimensional diagonal, we're only allowed to look at points that are sort of order n to the 2/3 around some one-dimensional straight line. And so that's why the secondary coordinate fluctuates on this n to the 2/3 scale. Okay. And so the story that we expect is at first order, what you see is a constant. And the constant is just proportional to the main distance, t minus s. And at second order, so on this n to the 1/3 scale, what you see, or what you expect to see, is some 4-parameter random field L. Okay, and L itself should kind of be a metric-like structure in a continuum limit. Okay, so L is what's called the directed landscape, and so the goal is to, understand this object as best as possible. Now, everything I've said so far is purely conjectural. And for models like this, so first passage percolation, it's pretty much, it's very difficult to prove anything about this model that even comes close to approaching the level of precision we want here. But what saves us is we can tweak the model and look at a model where we still expect sort of similar behavior in the scaling limit. But the new model we're going to look at has exactly solvable structure, and so we're actually going to be able to prove these things. Okay. So this is the new model. There's a couple of models you can look at. The one that I like is, one of the nicest models is what's called Poisson last passage percolation. So this here we're going to do the following thing. So I'm going to start with a Poisson point process on the plane. So just homogeneous rate 1. I think in the particular scaling that I'm with, it's a rate 2 Poisson process, but it's not so important. And then we're going to assign path weights between points. Okay, so in Poisson last passage percolation, we have a distinguished time direction and a distinguished space direction, and paths are only going to be able to move forward in time. And the weight of a path is just going to be the number of points in my Poisson process that lie on that path. Okay. So here, for example, I'm going from, so my coordinates are like xf, where f is my time coordinate, going up to yt. Okay. Well, maybe why don't I go back once more? Okay, so then I want to assign something that looks a bit like a distance between these 2 points. So my distances, or Poisson last passage values, are only going to be defined when s and t are in the right order. Okay, so s always needs to be less than t. And what I want to do is, rather than looking at the weight of the shortest path, I'm going to look at the weight of the longest path, right? Because it's very easy to put a path in place that avoids all points. So I'm going to look at the weight of the longest possible path between these 2 points. But I need to also put a restriction on the paths, because otherwise I could have a path that arbitrarily goes back and forth and picks up as many points as I want. So I'm going to force my path to be 1 Lipschitz. Okay. So here's the more wordy definition. So I have a Poisson point process P. And for 2 points with the right time ordering, I say that their distance, or Poisson last passage value, is the largest possible path length. So this is the number of points on the path P over all paths going from P to Q, where I just take a supremum over 1 Lipschitz paths. So you can check that it's not hard to check, the supremum is always achieved. So just like in first passage percolation in our previous model, you have a nice notion of geodesic. And we expect all of the same scaling that occurs, all the same scaling we expect from a previous model, we can actually prove that it occurs here. So you can prove that geodesics wander back and forth on this order n to the 2/3 scale. You can prove that the distance between 2 points that are order n apart is a constant times n plus a lower order n to the 1/3 correction. Okay. And you should really think of this as a metric-like structure. So we've lost a couple of things that are, okay, so this is not dp is not a symmetric function, right? So if the distance from P to Q is defined, then we can't go back from Q to P. And the triangle inequality goes in the opposite direction because we're maximizing over paths rather than minimizing. But morally, it's a metric. Okay, so it's something we call a directed metric. And this turns out to be kind of so this notion of a directed metric is just basically something that satisfies a triangle inequality. And it turns out to be quite convenient because when we're going to pass to the scaling limit, even if you start with first passage percolation, your scaling limit will no longer be a true metric. Your scaling limit, at best, will only retain this triangle inequality. So somehow this object actually looked a little bit more like the scaling limit than the true metrics on Z2 that we started with. Okay, so here's a theorem. So this is describing the scaling limit of Poisson last passage percolation, and it's just basically exactly this heuristic that we had a couple of slides ago. So we're going to look at points that live in this scaling that we wanted. So I'm going to look at distances between points x, f, y, and t in this limiting scaling, where x and y are on this n to the 2/3 scale, and f and t are on the order n scale. And the result is that in this scaling, after we subtract off this big mean term, we converge in distribution to a random limit. Okay, so this is a 4-parameter field, which assigns distances to points in the same way that Poisson last passage did. So it assigns distances to points x, f, y, and t whenever the time coordinates are ordered in this way. So whenever s is less than t. And this, I should say, this directionality, so the fact that we can only assign distances in one direction, you might think that this is it's kind of reasonable to at first think that this is an artifact of the fact that our Poisson last passage model only assigned distances with time coordinates ordered in this way. But this is really something that is inherent because of the way in which we take the scaling limit. So even if you start with a true metric here, when you subtract off a very large mean term, there are two ways in which you can do this. You can either subtract off a mean term, which is symmetric when you change the roles of T and S. And what happens if you do that is you naturally lose the triangle inequality. Or what you can do is you can subtract off a metric, you can subtract off a mean term, which is positive when S is less than T and negative otherwise. And that's the natural way to keep a triangle inequality in the limit. But when you do that, you sacrifice the symmetry of your metric, and half of your distances will become infinite in the scaling limit. So this directionality is really a very natural structure that shows up here. Okay. So how to think of L? So L is the random function, but again, it's a random directed metric. So it has this reverse triangle inequality. Again, and this is just a convention. We have a reverse triangle inequality rather than a triangle inequality because we're looking at maximizing paths rather than minimizing paths. It has, so many of the marginals of L have exact formulas. So this is the most well-known of the formulas. So if you pick a particular point, or a particular pair of points, X, F, Y, and T, then the law of this is a shifted and rescaled Tracy-Whittem GUE random variable. Okay, so the Tracy-Whittem GUE random variable coming out of random matrix theory. So this particular result is the well-known Bike-Dief-Johansen theorem for the scaling limit of the longest increasing subsequence. So really what in some sense, what we're doing is we're looking at longest increasing subsequences in random permutations, but in some disguise as Poisson last passage percolation here. Okay. And so you, anytime you have a continuum scaling limit, we should ask maybe about the regularity as you vary the parameters. So this is, it's a true continuous function, but of course it's just like with a lot of scaling limits, it's going to be rough. This is a very familiar object as you. So we have kind of two types of coordinates. We have the spatial coordinates X and Y, and we have the time coordinates X and T. And as you move X or Y, what you see is locally just a Brownian motion. Okay, so the precise result is that if I fix 3 of my coordinates and say just move X, then on any compact set, the resulting, one parameter process of X is absolutely continuous with respect to Brownian motion on that same compact set. Okay, so it really is locally Brownian in quite a strong way. And this process is much stranger in time. So it's rougher. So in particular, Brownian motion is Holder almost a half. But if I move my time coordinates, then what I see is a process which is Holder almost a third. And we don't understand the time process nearly as well. Okay, so there's if you want to think in terms of exact formulas, when you vary the spatial coordinates, there are nice exact formulas. It's much harder to understand exact formulas when there's not really nice exact formulas when you vary the time coordinates. There are still some, but they're much more difficult to work with. And they don't describe the whole process. They just describe certain marginals. Okay. So morally, you can think that we've done the following thing. So let's compare. I think of, when I'm drawing the directed landscape, I think of it in the same way as Poisson last passage percolation. So we have a space coordinate, we have a time coordinate. In Poisson last passage percolation, you have a background noise, which is this Poisson process, and you are maximizing over paths moving through this noise. Okay. In some sense, what you'd like to say the scaling limit is in the scaling limit, what you're doing is you are what you'd like to say is that you're rescaling the noise. okay? And then you are maximizing over paths through some kind of continuum limit of your noise. Now we don't have a precise sense in which we're doing this. So all we can take the scaling limit of is the actual metric values, but morally that's what's happening here. And so with this in mind, you can, for example, just like you have path lengths in Poisson-Last passage, you should be able to define path lengths in the directed landscape, just like you have geodesics in the prelimit. You want to be able to find geodesics in the limit. Okay. So you do in order to define path length, you do the usual thing for going from metric to defining lengths of paths. So say I give you, why don't I go back to the one with the picture? Okay, so say I give you a path from P to Q. What I want to do is I'll just look at some partition of this path, and I'll add up all of the distances along this partition, and that approximates my path length, and then I take a finer and finer partition, and I get a length of the path. Okay. And so paths are just going to be like they were in Poisson-Last passage percolation. So paths are just functions from Ft to R, and I define path length by subdivision in this natural way. In the scaling limit, of course, you're going to lose this one Lipschitz constraint. So now we can assign lengths to arbitrary continuous functions. Okay. And we say that a path is a geodesic if its length is just the distance between its endpoints. Okay. So when we were first constructing this object, we proved the following thing, which is that if you fix a pair of points, P and Q, then almost surely there's a unique geodesic between these 2 points. Okay. So if you're thinking about one of these pre-limiting models, what this says, so if you think about Poisson-Last passage percolation, between any 2 points, there's going to be typically many geodesics. Okay, even if you restrict to geodesics that are linear between your Poisson points, there's still going to be typically exponentially many of these. But what happens is in this limiting scaling, all of these geodesics are essentially the same. So the difference between these geodesics is small. Okay. Is small, and so small that you typically don't see it in the limit. So for a typical pair of points, what you only see is one geodesic in the limit. Okay. But what's interesting here, and what I mostly want to talk about today, is that this is not true at every set of points. Okay. So you cannot say that almost surely for all pairs there is a unique geodesic. Okay, and this is kind of a classical thing that happens in a lot of models of random geometry, is points of non-uniqueness. Okay. And so the goal is just to understand, well, what is happening at these exceptional pairs? What can we say? Okay, so here are a few possibilities for what can happen. So these are maybe some of the most common things. Maybe I'll just try and explain what's happening, how you might imagine something like the second option showing up when most points are connected by a unique geodesic. And maybe I'm gonna attempt an annotation, but I don't want to draw too much because it's going to be a bit messy. Okay. So let me look at a single base point, and let me look at 2 different points at a common time. Okay. So the geodesic picture that you expect is the following. Okay. That these geodesics have a tree structure. Okay. And because you should imagine that you're moving through some sort of rough noise, there's not very many good parts of your noise. And so what you expect is that these geodesics are going to want to take advantage of the same good parts of their noise at the start until they kind of naturally have to move off because they're going to different points. So you have some common common stem that you actually see for these two geodesics before they move on. Okay. And if I draw some point in the middle, then points in the middle are either going to coalesce with the left branch or coalesce with the right branch. Okay. And so how would you get to picture number 2? Well, the idea for getting to picture number 2 is there's going to be some split point in the middle, where to the left of this split point, you coalesce to the left, and to the right of the split point, you coalesce to the right. Okay. And at that particular split point, you see a non-uniqueness event. Okay. So if you believe in this coalescent structure, you can fairly quickly convince yourself that there should be structures like this, these sorts of non-uniqueness points. Okay. So in terms of the other pictures, you could imagine that you get picture number 4 by playing the same game, but on both ends of the geodesic. So you kind of wiggle both ends and you get 2 bubbles. Similarly, if you now take picture number 2 and just cut it in the middle, then you've cut off the base stem and you get bubble 3, picture 3. Okay. So I'm going to call the set of all geodesics from P to Q the geodesic network from P to Q. And our goal is going to be to try and classify what sort of things we see in this directed landscape. And again, you should think of these as, if you prefer to think about the discrete models, think of these as shadows of structures that will stick around in the scaling limit. So these are sort of structures that are fundamental to the discrete models. So they're not things that are happening because of exact microscopic properties or are just happening at small scales, but there are things that are kind of fundamental structures of the type of random geometry that we're studying. And I think I should erase everything now. Okay. So the theorem is that there are exactly, up to some notion of isomorphism, which I'll describe in a second, there are exactly 27 possible geodesic networks that you can see. And this is what they look like. So some of them we've seen before and some of them are new. So for example, picture 2 is the one that we argued for on the previous slide. We also argued for picture 3 and picture 4, or picture 4 and picture 5. And some of them are quite a bit more exotic than others. So picture 27 is more exotic and harder to argue for than picture 2. And indeed, like the way the proof goes is there's not an ad hoc argument for every one of these 27 things. That only is a good idea for dealing with a couple of them. And as you can imagine, some of them are going to be rarer than others. So I'll talk about that in 5 to 10 minutes or so. All right, so let's try and understand what is going on here. How did I get these 27 things, and what is the notion of isomorphism? Okay, so what should we do? We should turn geodesic networks into graphs, right? So a geodesic network, you naturally think of it as a directed graph, right? So I have a source vertex, which is my base point P. I have a think vertex Q, and then I'm going to turn all of my branch points into interior vertices, and I'm just going to draw arrows between them. Okay. And so the first natural notion of isomorphism would be, say, 2 geodesic networks are the same if they have the same directed graph. The other thing, and that's basically going to be the notion, except I want to add one more possibility, which is, so if you think about all the models we've defined, if I take the directed landscape, or if I take any of these prelimiting models and I flip it on its head, then there's no fundamental difference in what I've done there. Okay, so there's a time reversal symmetry for the directed landscape, and so I should build that into my notion of isomorphism. So in particular, if I take one of these directed graphs and reverse the directions of all of the arrows, so if I take the transpose, then I should call those two things isomorphic. Okay, so I'm going to call these two guys isomorphic in particular. Okay, so here are some examples of isomorphic networks. So on the picture, the pair on the right, these guys are isomorphic because they are transposes, even though they are not the exact same directed graph. I want to point out something about the structure of the pair on the left. So the pair on the left are not the same as planar graphs, but they are the same as graphs. Okay, so I'm throwing out the planar structure. So everything here is living in the plane, but but I've chosen to forget the planar structure. If you want, you can keep it around, and your count changes slightly. It's not so important. It's not really telling you anything more or less fundamental if you keep around the planar structure. Okay, so what are the rules? And the rules tell us a little bit about, the rules will kind of hopefully, tell us something about random geometry as we understand these. So the first couple of rules for when you see one of these things in the directed landscape. Okay, so the first two are not very interesting. So every one of these directed graphs that shows up as a network has one source vertex and one sink vertex. And if that's clear from how we structured this, they're all planar because things are taking place in the plane. They're all loop free, okay? Because you need to move forward in time. You can't sort of come back to yourself, okay? It's actually less obvious that when you look at all geodesics from point A to point B, that the resulting structure needs to be finite. It's really not very clear at all, but it's certainly nice from the point of view trying to understand what these things are, and it turns out to be true. Okay. And now let's now let's look at the three kind of interesting conditions. So the first interesting condition says that if I take my graph and I remove, and if I look away from the source and the sink, then I never see a cycle. So in particular, the network that I have just drawn is not allowed. Okay. So what this says is that in one of these geodesic networks, I can see bubbles, but they never happen in the middle. They only ever happen at the top or at the bottom. And the way that you can imagine this is if there were a bubble in the middle, you could take your point at the top, wiggle it a little bit, take your point at the bottom and wiggle it a little bit, and see the same type of network, okay? And in particular, you could wiggle these points so that they become rational and see the same type of network. But rational points for us should be completely generic, and generic pairs of points are connected by a unique geodesic. So this is a very hand-wavy argument for why you shouldn't see these things. You need to make precise sense of your ability to wiggle the top and the bottom, but morally, that's why you shouldn't see bubbles. So the presence of interesting networks can't come from things happening in the middle. It has to come from things happening at the top and at the bottom. Okay. Next point, and this is also about the middle of the network being generic, is say I give you a geodesic network. If I look at an interior vertex, like this one here, then this vertex has to have degree 3. And what this means is that in your network, you always have binary branching. Okay, so you never see anything like this, for example, and you never see anything like this. Okay. And this, again, think of this as being a generic condition for the middle of your network. So in this, so the moral of points 3 and 4 is interesting stuff is happening at the top and at the bottom, but in the middle, you should imagine the most typical structure for how things can happen in random geometry. And the most typical way for geodesics to come together in branch is if that always happens with binary branching. Okay. Okay, so for the final point, points 1, 2, 3, and 4, we haven't yet really put any conditions on what happens at the top and the bottom of these networks. The final thing that happens is at the top and the bottom, you have at most degree 3 coming out of P and at most degree 3 going into Q. So the idea here is, well, your bottom and your top can be exceptional, but they can only be so exceptional. So there's sort of some restriction coming from ultimately like some Hausdorff dimension type computation about how exceptional your top and your bottom of your networks can actually be. And it turns out that the exact right condition is at most 3 branches coming out of the base and at most 3 branches going into the top guy. Okay. All right. So that's some idea of what you see. And maybe I should, if I go back. So once you have these 5 conditions, then this is a pretty easy exercise to just kind of enumerate what you get. It's an exercise for an undergraduate class or for someone with some amount of patience who's finishing up the last couple of pages of their paper, that sort of thing. Okay, so once you understand what's there, you want to understand, so you sort of have your, I don't know, the idea is you're a botanist and you have just discovered a new land. And the first thing is you write down all of the plants that you see, but then you want to say how common each of these types of plants is. So we should understand some sort of Hausdorff dimension for these networks, okay? And naturally we're living on, so the directed landscape is naturally a function on R4. So you could ask about the Euclidean Hausdorff dimension, but if you're working with an actual metric, you're working with a metric in the continuum, it's going to be better to think about the Hausdorff dimension defined from that metric itself. Okay, so we'd like to do this for the directed landscape. But the difficulty when we do this is that the directed landscape is not a true metric. And so in particular, because it's not a true metric, we can't just directly define Hausdorff dimension. So we're going to define some sort of proxy, okay? And the thing to remember is that the directed landscape is Holder almost a half in X and Y, because there it looks like a Brownian motion, and it's Holder almost a third in S and T. So between those 2 points, we can suggest the following distance. So let's put 1/3 powers on the time coordinates and 1/2 powers on the space coordinates and call that our distance. And when we do this, this is a nice distance. So in this distance, the directed landscape becomes almost Lipschitz. So it's like Holder 1 minus epsilon for every epsilon. Okay. And the other thing that happens is we've turned R4 into a 10-dimensional space. Okay. But somehow this is the right thing to do from the point of view of studying the directed landscape. Okay. And so when you do this, you can actually get a nice formula for the Hausdorff dimension of the set of points where we see any particular geodesic network. So given a geodesic network G, okay, so one of these 27, the Hausdorff dimension in R4 of the set of points whose network is G is given by this particular formula. Okay. And again, something you can check. In all of the examples that we have, it's not hard to check that this is always non-negative. There will be certain cases when the right-hand side here is 0. And in this case, we should say a little bit more. So when the right-hand side is 0, you can say that the set NL of G is exactly a countable infinite set. Okay. And again, all of these results are almost sure. So there's sort of, there's kind of mixing and ergodicity properties of your landscape, or any kind of thing you say about the whole structure is going to be almost sure. So maybe as a sanity test, you can put in the statistics here for our trivial network. So let's draw the trivial network. I have two vertices connected by a single edge. So V equals 2, and the degree of P and Q are both 1. So I get 2 plus 1 plus 1 over 2, which is 2. So I get 12 minus 2, which gives 10. And 10 is the dimension of the whole space. Okay, which makes sense because almost every, in a Lebesgue measure sense, almost every pair of points looks like the thing that I just drew. Okay. And you can use this kind of theorem to see, if you look at the set of graphs, you can pretty quickly see which ones are going to be more common than others. So the ones that have more complex branching are, as you would expect, rarer, and rarer by some amount that is captured in the captured by Hausdorff dimension. Okay. All right, maybe I have, so I have 7 minutes left. I want to try and say a little bit about where, maybe I'll try and say, maybe I'll skip this. Actually, I can say, I'll say a little bit about where this formula is coming from, or try and just.
You're welcome to take 10 minutes, by the way.
Okay. So the philosophy that's, for me, the philosophy that drives a lot of this, there's a mixture of a couple of things that go into actually proving this. There's something which I always, my perspective is always to shy away from the exact computations and focus on some kind of geometric intuition. So that's what I'm going to do here. The main geometric intuition about rounded geometry is coming from coalescence. Okay. So this is this idea that I mentioned before, that if two geodesics, they have points starting fairly close together, then they'll typically coalesce. And in fact, you always see one of two things. Either geodesics will be completely disjoint, or they will share some stem. And in particular, if I take base points and wiggle them a little bit, then the geodesics won't change very much. They'll only change near I should expect that they only change near the base. But other than that, I see the exact same picture because of coalescence. So this is the first one is obviously a doodle. The second one is a simulation that I, again, did not do myself, but pulled from someone online. This is all geodesics in a model of first passage percolation from the origin to some outer boundary. Okay. And you can see what coalescence says is that there aren't actually very many good paths leaving the origin. There's a couple, but basically you have sort of a lot of branching happening right near the boundary, and then everything kind of comes together. Okay. And so the intuition from a picture like this and sort of the other picture is what we were saying before. At the end of a geodesic network, you might have weird things happening, but the interior, everything should be generic and have coalesced together. Okay, so what's the story? The ends of the network are special, but the interior is generic. And so the rarity of a particular network should be based on the rarity of the end configurations. Okay. So these end configurations are called geodesic stars. Okay. So we have a geodesic star at P. I'll call this a geodesic 2 star because we have 2 disjoint geodesics coming out of P, and we have a geodesic 3 star at Q because we have 3 disjoint geodesics going into Q. Okay. So what we should do is, prior to classifying all networks, let's try and understand what happens with stars. So this is a simpler thing. We just need to understand what is the chance that we have K disjoint geodesics coming out of a particular point. Okay, and this is something you can do with Hausdorff dimension. You can actually do an exact Hausdorff dimension computation. a mix. I won't go into the details of this. Again, it's a mix of some stuff coming from the exactly solvable world and some stuff coming from planarity, geometry, and coalescence. So if we're looking at R2, in our 1/3, 1/2 metric, R2 becomes a 5-dimensional space. Most points in this 5-dimensional space are 1 stars. Some of the points are 2 stars. Some of the points are 3 stars, and you never have any 4 stars. So now let's use this theorem to try and guess a Hausdorff dimension formula for an entire network. So based on the theorem, we have a kind of obvious upper bound, right? Which is that if I'm looking at my starting point and I'm looking at my ending point, I can just count the Hausdorff dimension of all the 2 stars and the Hausdorff dimension of all the 3 stars. And these networks are going to live in the product of those 2 sets, right? And so the Hausdorff dimension will be bounded above by the sum of those 2 initial Hausdorff dimensions. Okay. But now I claim that there is a penalty on top of that. And here's how you should think of this penalty. Maybe I can. So there is a penalty of 1 Hausdorff dimension for every single interior face of the geodesic network. And the idea is as follows. So say I take an arbitrary 2 star at P and an arbitrary 3 star at Q. And because my interiors are generic, if I'm trying to connect them up, I don't really have any choice as to what I put in the middle. So I have my single brick that I can just put in the middle. And then I want to ask, when I put that single brick in the middle, did I get a geodesic network? And the test there is basically, did I manage to do something where all of the lengths of these paths ended up being the same? Okay. And typically the answer is going to be, well, no. Like say I have independent lengths, x1, x2, x3, x4, x5. And all my lengths in the middle are 0. If all of the xi were just IID uniform, the chance that everything here is going to have the same length is essentially 0. But you can ask, what is the probability that, what is sort of the probability that all of these lengths are kind of within epsilon of each other? And essentially what you're doing is you need to have that a bunch of paths will have the same length, okay? And what ends up happening is you get a system of, you get a linear system, right? Okay. And the number of constraints is exactly the number of interior faces, because basically what you need to have happen is if I take the right route around an interior face versus the left route, then these need to have the same length, okay? And so you get a penalty, a 1-dimensional penalty for every one of these interior faces. Okay? It's a bit of a hand wave, but that's the idea. So this, if we know our 2 star and 3 star dimensions, then the Hausdorff dimension of the whole network should be given by this kind of formula. Okay. So this is the story. It should be the Hausdorff dimension for a set of geodesic networks whose source and sink vertices have degree k and L should be the following: dimension of the k stars plus dimension of the L stars minus the number of interior faces. And that has a simple formula based on the K star L star theorem. Okay. All right, so I think maybe I will say only, I have maybe a couple more slides about other models of random geometry, but I'm just going to skip all of the background there, because I always make way too many slides with the idea that if I end up going really fast, then I have stuff to say. But I want to just mention one thing for those who are aware of these models. So there are other models of random geometry that are also nice. These models are, say, the Brownian map, or more generally, Liouville quantum gravity. And Liouville quantum gravity is a model which is parameterized by some gamma between 0 and 2. It's again a kind of continuum random geometry model. It turns out to be a true metric. You have geodesic coalescence, and so a lot of similar structures you expect to see. Okay. And some of the things that I've been saying, sort of the soft, some of the soft parts, it's not completely clear which of the arguments are soft and which are hard. A lot of the soft arguments should go through in these models. And so based on this, you can kind of follow the heuristics and think, well, how many geodesic networks could you potentially get in a model of vehicle quantum gravity? And what it suggests is that there are 3 possibilities. You either see the same 27 networks that you see in the directed landscape, or else maybe you see 29, or maybe you see 28, depending on the value of gamma. Okay, and these are the 2 that are potentially there for certain values of gamma. So when gamma is very close, when gamma is close to 2, you see 27. And as gamma goes all the way down to 0, you should see all 29. And then there's some middle range where you should see 28 again. So if you're not aware of these things, just think of it as a curiosity or a new word. All right, I will stop there.
Thank you very much for a beautiful talk, Duncan.
Thank you.
Can I ask if anybody has any questions? Maybe I can get started by asking a very naive one. So suppose you've got one of your 27 pictures. How much can you say about the joint law of the distances within them?
Maybe do you have a particular, why don't I go back to one of the pictures?
Maybe take the simplest, sort of not just straight line.
So why don't I go back to the simplest picture that I had here? So say you have something like
Say
this.
that one, yeah.
So what so you want to say something about like the joint law of going from A to B and then B to
where's the split, if I can put it that way?
Okay, so it's not something that I have analyzed. The location of the so if you look at say the location of the branch point. If you look at the location of the branch point, so say I'm starting at the time 0 and ending at time 1, which you can do with this particular network. So you can ask about like both the space and time location of the branch point, and the law of that, for example, will be absolutely continuous with respect to Lebesgue measure on the strip. I don't know how much more you can easily say about that law. And similarly, like if you look at the distance from between the 2 base points and the branch point itself, all those 2 distances will both themselves be, absolutely continuous with respect to Lebesgue measure as well. But in terms of exact statistics, so there should be something really interesting, but it's not clear what it is. One thing you can say is one thing that you can say around branch points is you can zoom in on a branch point and ask how the law of the whole landscape changes. That's something you can get around branch points. There's some natural structural change that happens there. But even then, it's not kind of a particularly precise thing. I mean.
Thank you. James, you look like you're about to ask a question.
Yeah, I was just wondering about, so can you, if you ask how many sets of semi-infinite geodesics you can get in a given direction from a given point, does it basically look like just one end of the networks you can get, or is there something more exotic that can go on if you're looking at infinite paths?
No, the story is a bit simpler, yeah, because I think I didn't write it down for semi-infinite paths, but basically what you can get for semi-infinite paths is you can for semi-infinite paths you can go so your base point can have some arbitrary degree, 1, 2, or 3, and your direction off to infinity, assuming you want to look at sort of common directions.
Mm-hmm.
In every direction, there's either a unique, so for typical directions, all geodesics in that direction coalesce, and then you'll have exceptional directions where you'll have exactly 2 you'll have like a one left option and one right option for how to go off to infinity. So basically what you get is, if you look at this picture, if you imagine one of these points at infinity, the things that will be allowed in that setting are anything where your top point does not have degree 3. That's the idea.
Thanks.
Brett, do you have a question that you want to ask, or I can ask it for you if you prefer?
Again, I should say that's not proven. I should probably, I think it is. I think there's a paper of, there's a recent paper of Ofer Busani, which I think probably completes that. Yeah.
So Brett Kolesnik has a question in the chat. So did you say already the cut locus, is it a fractal or Brownian tree? He's having sound.
Hold on.
I can try to. It's going to echo. Yeah, I can't talk.
Sorry, did you want to ask a question or?
Oh, sorry, it was echoing. I think we figured it out. The cut locus, so it's like the set of all points. You have a reference point. You have the set of all points that have at least 2 geodesics to that point.
Mm-hmm.
Can you say anything about the structure of that set? Is it is it a Brownian tree, or is it something like that?
It is not. Okay, so the exact it is not a Brownian tree, because those are, you don't see, the Brownian trees aren't exactly the types of objects that you see in this world, but it does have there is one exact identity that happens in the directed landscape. So if you look at all, which it's not precise in the, so if you look at all geodesics going off to infinity in the same direction, okay, so this forms a tree. And if you look at the dual tree of this, which is essentially like your cut locus, then this dual tree is equal in law to the original tree after you flip. Does this help?
Yeah, okay, thanks. I guess the other thing you could look at is you could look at the collection of all points that are strictly inside of a geodesic, so not an endpoint.
Mm-hmm.
So for the Brownian map, Jason Miller and others showed that it's dimension 1. Do you have something like that?
Yes, yeah, you do. I mean, so that in general, what you have is like the analog of this result is that if you look at the interiors of all rational geodesics, then this is the same as the interiors of all geodesics. So this is, again, like I think of it as like a strong version of the coalescence property. So in particular, like for one thing that you have in this world is if you take any geodesic, you can approximate any geodesic in a strong overlap sense with a sequence of geodesics at rational endpoints. So in the sense that you can take a sequence of rational points converging to not only where the rational points converge to your base points, but also the geodesics between those rational points will eventually overlap with your target geodesic. So for example, say I'm looking at one of these 27 guys, say I look at this one over here. If I take rational points approaching the base points from the right, eventually I will completely overlap with the right side. Similarly from the left. And moreover, if I kind of choose my rational points carefully to be close to this middle geodesic, I can also get rational geodesics, which will choose exactly to overlap with the guy in the middle.
Yeah, so I think this is just exactly analogous to what Jason Miller did in the Brownian map, and exactly how he classifies the geodesics too, right? It's the same argument, you know, generally. Different environment, of course, but same strategy, right? Yeah.
Mm-hmm. Yeah, so I was gonna, so so the nice thing is, in terms of the Brownian map setting, for the Brownian map, in order to get like a full geodesic network classification, a lot of the tools seem to be there. So I think of course, these are the slides that I skipped, or all the ones that are actually about the Brownian map, but maybe I'll leave it here. So there's, in terms of Hausdorff dimension upper bounds on all networks, there are results of these Miller and Chan results give you Hausdorff dimension, upper bounds on all of these guys. In terms of the Hausdorff dimension of these K stars, there are upper bounds coming from Miller and Chan and matching lower bounds of Le Gall. And so between all of these things, you should expect to be able to get the same sort of exact classification of the Brownian map. Now, there is still some extra stuff which I think is maybe harder in that set, or at least different in that setting. But I think all the tools are there.
Great. That seems like an excellent place to wrap up. I'm going to just stop recording and then invite everybody